Alrighty then, let's start streaming now. Okay, so this lesson is about straightening curves. So let me just write that out. Straight, G-H-T-E-N-I-N-G, curves. Yeah, my handwriting getting really bad. Alright, let me just type that out so it looks better. S-T-R-A-I-G-H-T-E-N-I-G, curved. Right? Alright, so let's talk about this topic called straightening curves. The objective of this lesson, and let me try this in green. Objective is to apply logarithms to problems involving the transformation of a given relationship to linear form. All right, that's what we're going to be doing in this lesson. Okay, so how do we do that? All right, I'm sure that you have already established yourself in some form of science field, and in some of the real world problems or some of the experiments that you do, you'd notice that the variables can be related by an exponential form or a power form, right? A power law form, right? These relationships would tend to appear curved when you put it on a graph. By taking logs on both sides, what you can do is you can actually transform those curves into straight lines, and that can make it easier to analyze information by just determining your gradient and your intercept. So what we're going to do in this lesson, I'm going to do an explanation, show you about 2 examples for each of the explanations about how it can be applied. And what we're going to do is we're going to try and show you, well, I'm going to try and show you how to identify the intercept and the gradient. Now, the intercept and the gradient, we can learn about that later when we talk about coordinate geometry, right? For now, all you would need to understand is that there's a general form for a straight line equation, and that general form has 2 important values in it called the gradient and the intercept. And what we're doing in this lesson is we're converting exponential form and power law form into a straight line equation so that we can easier get the constants that we need by simply measuring the gradient and the intercept, right? So it's just to make our work easier, we're going to apply some maths to the knowledge that we have, right? So let's first start off, that's green. All right, let's first start off with the exponential form. Exponential form. Why are we starting off with the exponential form? I don't know. I just prefer to choose it that way. So let's consider y equal to ab to the power of x, where y and x are variables, right? These are the 2 quantities that change with the relationship, so manipulated and responding variable, that kind of thing. Then we have your constants, a and b. A and b are constants. Right? So now we have your constants, and according to what we just did, we're going to take logs on both sides. So we're going to say taking logs both sides, 1 becomes log to the base of y equal to log of a b to the power of x. And we can use the product law, so using the product law of logs, we can simply make this look like this: log y equal to log a plus x log b. And I'm sure you know how I bring down that power of x. And what I want you to do, well, you know what, let me not do it that quickly. Say log of b to the power of x, right? And just so that anybody following along the video can see, but log base to the x, b to the power of x is just simply x log of b. So we can simply rewrite this as we see fit. So it's just log y, and I'm just going to switch the positions. So I'm going to say x log b plus log a. Right. So we get there now. Everything is in logs. Now I want to write out the general form for a straight line. Right. So I'm going to write this in green is good. So the general form for a straight line is y equal to mx plus c. Now, usually everything is in common letters, but because I was a little bit in a rush and I decided to use these common letters here, I don't want to go back and erase everything and then put capital Y and capital X. So we'll just put capital Y and capital X here. But know that usually this is stated with common letters. All right, so general form of a straight line, y equal mx plus c. Now we can say comparing, well, comparing what we can see is that I'm going to circle some things instead of highlighting it over. I'm going to circle this and this. I'm going to circle this and this. I'm going to circle this and this. And then I'm going to circle this and this. The value over here, x, and the value over here, x, is the same thing. This is a variable. This is a variable. This is a variable. This is a variable. Okay, so when I compare these two and I circle those, you can see right away that, you know what, let me write it in, yeah, in different colors. So like you can see that the y is equal to log of y, right? Let's do the pink now, and we can see that m is equal to the log of b. We can see that x is equal to x, and we can see that let's say c is equal to log of e. Now, these two things on the corner here, these are the important ones. This is your gradient, and this here is your y-intercept. Right? So that's gradient, that's y-intercept. Good. And these are the values that you'd just be interested in to get these little constants that you have over here. You can use your power form, change this into a power form to be able to get this correct or figure this out. And I'm just showing you that once we plot this against this, we get a straight line. We can read our gradient and intercept very easily from a straight line. And all we have to do is use those gradient and straight line to get the unknown constants in our power equations up here, or exponential form equation up here, right? And now let's show an example of where this can be useful, right? I'm going to show two examples, okay? Let's say example number one, a country, UN, that looks like the same letter in both cases on the right letter, COUNTRY, country's population. A country's population follows the law P equal P naught E to the K T. All right, where P is the population after T years, right? I'm going to highlight this here as one of the variables as well. I'll put that here, right? P naught is the initial population, and K is the last one, is the growth constant, right? So let's look at this kind of example here now. So first off, we start off given P equal to P naught e to the kt, and I'll call this equation number 1. What I'm going to do is I'm going to take natural logs. I'm taking natural logs because look at this. This here is an e. If I take a natural log, I'll get rid of that e. So let's do this. So taking natural logs both sides, 1 becomes ln of p equal ln p naught, put it in bracket, e to the power of kt, close the bracket, right? So we're using product law of logs here now. So using the product law of logs, we'll get that ln of p is equal to ln of e to the power of kt plus ln of p naught. All right, we can bring down these powers here very easily, this k and that t, right? So we're going to get that ln p is equal to kt. And now remember, ln of e is just simply 1, so I'm just going to have 1 inside here. I'm not going to put it back. This here is equal to 1, right? So then plus ln p naught. And notice you have your variable here, and then you have this constant here, the growth constant, and this constant here is the intercept, right? So in this situation, so the gradient is equal to that growth constant k, and the intercept, you know what? The y-intercept is equal to ln p naught. All right, and from there you can just simply use this method, right? So I'll just put a note here. This is a method that can be used to estimate the growth rate k, right? So you can estimate the growth rate k just by simply reading off the gradient or calculating the gradient of that straight line, which is much easier than doing it with a curve, right? It's much easier than doing it with a curve. Okay, let's go on to the next example and same kind of situation. Oopsie, let's put that as solution. Right. Same kind of example. Let's do another example. Example number 2. The activity A of a radioactive sample decreases according to A equal to A naught e to the minus lambda t, right? Where lambda is the decay constant, right? Lambda is the decay constant. Okay, let's look at this and see how we can actually convert this into a straight line equation as well that we can use to calculate this initial activity and this here, this decay rate, that negative pi there, sorry, negative lambda, right? So we can say given this equation here, you know what? I can just simply copy and paste this equation. Okay. Control C, come down, Control V. Oh, lovely. Put this here, drop this in Y. There, good. And then we have here equation number 1. So given this, then taking again we have an e, so take natural logs. Taking natural logs, we get that ln of a is equal to ln of a naught, and no, let me just not do it. E to the minus lambda t, close bracket, right? And then I can say using the product law of logs using that product law of logs, what we can do is we can actually separate that a little bit. So we have ln of a equal, and I'm going to bring this over on the side. So I have ln of e to the power of negative lambda t, and then plus ln of b is 0, right? And then from there, all I can do is I can get rid of that. So I can say ln of a is equal to negative lambda t. Again, remember ln of e is just simply equal to 1, not 0, equal to 1, right? And then plus ln of a naught. Okay, so that's it there. That's done. Okay, and now we say using, you know what? No. So we have that there. Oh, right. Now let's circle again, right? We're going to just write this y equal mx plus c. We're going to compare again, right? Let me just write this big up. X and then plus c. Right, we're going to write this again. Notice here, and I'm not going to write everything again. I'm just going to write this part here. Notice that our gradient is equal to our root rate. Notice that our intercept is equal to this ln of the initial activity, right? So let me just write this here, where gradient is equal to negative lambda, which in a sense is going to show decay, right? That negative gradient is showing decay. And then the y-intercept is equal to ln of a naught, right? Very easy. And what do you think you can use this for? This here is used in anything that involves radioactivity. So this can be used to determine the half-life of radioactive isotopes, such as in medicine and archaeology, right? So when you think about things like how old something is and use carbon dating and stuff like that, this is part of the formula that they use. So this is very useful in physics, right? So two physics examples. This is physics, well, and that's not physics. I could probably use in biology. That's okay. Right? So two examples. Let's go on to the next form that you'll experience, which is the power form. Okay? So, so I'm just going to write here power form. Power form. So we consider y equal to ax to the power of n. Now, this here is definitely something I don't need to do again, because quite frankly, you saw that already up here. We just take logs both sides and we write it in the form of y equal mx plus c. I took logs here before. Let me take lns here now, right? It's not that, it doesn't matter. It doesn't matter, right? So where a and n are constants, right? And y and x are variables. We're going to say taking natural logs both sides, we get ln y equal to ln a x to the power of n. And then we're using the product law of logs. So using the product law of logs, we're going to end up splitting this up a little bit. So we will get something like ln y equal to ln x to the power of n plus ln of e, right? And if I expand a little more, I can get ln of y equal to n ln of x plus ln of e. And again, just watch this. This here is your y, this here is your m, this here is your x, and this here is your c, right? So again, we're able to see that our intercept and gradient, let me just add the next page. So our gradient ended up in this case as ln A, right? Ln A. And the gradient is represented by m. Have not been writing that. I just made the assumption that everybody knew what that is. Gradient m is equal to ln A, right? And then we have the intercept, y-intercept. Y-intercept c is equal to ln, oh, sorry, not ln, is equal to n. No. Why am I writing craziness? This is n, and this is ln A. Gosh, right? Because look at it, it compares here, right? Variable, 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 variable. Gradient is with this x variable, and this here is the intercept, right? Maybe I should really go back and write up all of this, right? So that you will have this here. So this here is m, this here is c, right? Let me go back up again. This here, oopsie, yeah, this here is m, that's a k, and this here is c, that's that. And let's go back up again, right? Well, I already put m and c as gradient and intercept, so you shouldn't have a problem. Waste of time. Where was I? Right, so that's power form, that's comparison, that's a gradient. And notice it's a ln x, ln y kind of relationship. So that means if you plot the ln y versus the ln x, you're supposed to get a straight line and you'll be able to easily get your m and your c. Let's do some examples so you can see what this can be used with. So example 3. All right, so let's say we will look at some physics problems like Boyle's law. So in a fixed mass of gas at constant temperature, the pressure P and volume V are related by a power law of the form P equal to AVN, right? What we're going to do is we're going to use logs to write the linear, which we was doing all the time, linear form, right? That's what we're doing all the time. So we can say something like given P equal to AVN, given that taking logs both sides, then log of P is equal to log of A V to the power of N, and using product law, so using the product law of logs, using that product law of logs, we're going to get that log of P is equal to log of V to the power of N plus log of A. And we can just write that log of P equal N log V equal log, sorry, plus, not equal, plus log A, right? And that's that, okay? We can see right away that your variables are this and this, right? Log of P, and that does our variables. We can see that this here is your gradient, and we can see that this here is your y-intercept, right? I keep saying intercept, and I mean y-intercept, so don't fault me for that, all right? I keep saying intercept right now. Later on, I'll be very specific about it because we have to do coordinate geometry. Let's look at the last example, okay? Example 4. Let's say that the period t of a simple pendulum You know, in physics, I think you would have an experiment like this to do, where you would swing a pendulum and find the time period, length of the pendulum, and all of that, and then you plot it on a graph. I think you'd have to use logs to solve that as well. Time period t of a simple pendulum and its length L are related by the power law T equal to A L N, where A and N are constants. Right. And from there, we can just simply take logs both sides. So, last page. So, given T equal to A what by? AL to the power L to the power N. Then by taking logs both sides, we get what? We get log of T equal log of A. I'm not gonna do that. I was just gonna skip all this. Using, I feel that if I repeat it enough, that you'll probably remember it. Of logs. And we get log T and N log L plus log A. Right, that's it. Okay, that's it, nothing else. And we compare it again to y equal mx plus c. And you can see this here is my gradient. You can see that this here is my y-intercept. And that's it, right? Once you're able to take logs and you're able to do so properly by using all the laws, these non-linear lines that you would end up with when you're doing certain types of experiments or certain types of work, or you establish certain relationships that have these little curves, you can use logs to make them straight. And once you do that, you would have no problem getting your gradient, your intercept, and then you can substitute that gradient and intercept, which is your constant values, like in this case your A and your B. You can substitute it back into the original equation and be able to have something that you can work with then. All right, so that's it for this lesson. If you have any questions, comments, issues, let me know, and I will see you in the next lesson. Good luck. Well, that's it. Good night. Bye-bye.